Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and we will continue our discussion on the conservation of energy. So what we have is energy conservation. Okay. So for a central field, we have F is m times Fr r hat. For a central field, F is conservative. F is conservative. Okay, and well, I think we'll specifically. I think we haven't given such an example so far, but we'll see a little bit later that how come for a central field the force field is conservative. But for the time being, let us just assume this statement. Okay, so the force field is conservative. So the moment we talk about force field being conservative, we can associate a potential with regards to the force field. So with potential energy m times Vr, where f of r is minus dV dr. Okay, so with potential energy m times Vr, where f of r is minus dV dr. So then, of course, with the energy conservation principle says, the law says that the total kinetic energy plus the total potential energy, the potential is coming from this force field, is the total energy E, and this is typically a constant of the system. So my kinetic energy plus the potential energy, the total potential and kinetic energy, the sum is a constant, which is E. So then if we want to write this conservation law in the polar coordinates, it translates into the following relation. It says that, so when we have if we want to write the kinetic energy in polar form, we will have the kinetic energy of the center of mass. So this is half r dot square, that is the kinetic energy of the center of mass, plus half r theta dot square, which is the kinetic energy of the body about an axis passing through the center of mass. Okay, and this is my total kinetic energy plus the potential energy is, of course, in a central field is V of r, and this is equal to E. Okay, so that is what we have. So then let me call this as my equation number 2, and my equation number 1, my 1 was the conservation of angular momentum. So my equation 1 was the conservation of angular momentum. My equation 2 is the conservation of energy. So then of course 1 and 2 are what we are going to use to describe our planetary motion. So this is the basis. This is the basis of orbital motion. Okay. So then we can rewrite. So if we use 1 in 2. If we use 1 in 2, we get that theta dot is L over r square, and from here we can plug it into our energy equation to see that this is r dot square by 2 plus r theta dot square plus Vr is equal to E. Right? And then what we have is that from 1 and 2, well, I think we haven't written anything new here. So this is the same as 2. So from 1 and 2, we can rewrite that my energy equation is half r dot square. I needed to replace the second term. So half r dot square plus Vr plus L square by 2r square is equal to E. Right? So half r dot square plus Vr plus L square by 2r is equal to E. So this is the equation for radial motion. Okay. Okay. So from 1 and 2, we have found the equation for radial motion. So then let us now rewrite this equation in a little bit different manner. We see that we can club these two terms into a single potential known as V star. Right? So we see that this is half r dot square plus V star r is equal to E. Right? Well, there is a slight change here. This is going to be r dot square by 2 plus Vr. Let me call this as Vr. Yes. So here it is. So hold on. So let me bring in the 2 here inside. So what we have found is that r dot square by 2 plus Vr star is E. Notice people who are watching this equation, notice that this is very similar to the conservation principle in 1D, right? As if the motion is only along the radial direction, right? In 1D it was x dot square by 2 plus v of x is equal to E, right? So here we have clubbed the two terms to define an effective potential V star, right? So what we have is, what have we got? Okay, so this is what we have. V star is the effective potential. Okay, so then let us see the physical impact of this equation through some diagram. So what have we got? So let us say that our total energy, so typically the total energy of the system is a constant, so that is E. And let us say my diagram for V star is as follows, right? So this is my V star versus R, of course, right? And what have we got here is, right? So we have this is A and this is B and this is C. So these are my 3 points A, B, C. And let me just tag 2 regions here. Notice that if we are in this first region between A and B, we'll see that the motion is typically bounded, right? And if we are in the second region between C to infinity, the motion is typically unbounded. Okay. So what have we got here is, let me rewrite our conservation principle. R dot square plus Vr star is equal to E. Now notice that this quantity is non-negative. So which means that our potential Vr star, our effective potential, has to be less than equal to E. Right? So which means that let me say that this is our E here, right? So which means the following. So E is here, and our potential V star has to be less than equal to E, right? And what have we got here is effective potential, and so yes. So since this is our kinetic energy, our kinetic energy is always non-negative. Our potential energy is bounded above by the total energy E. So now based on this inequality, we can conclude 2 regions. One is the region of bounded motion, bounded motion, that is P oscillates within the range, P oscillates within the range A comma B, and in this motion oscillates within the range A comma B, and in this motion we have that the motion RT, the variable which is defining the motion is RT, is periodic, right? Later on we'll see all these details in a mathematically rigorous fashion. So if the motion is within this well, we expect that the solution is going to oscillate but eventually stay within this well. And in the second region, which is the unbounded motion, the motion P is in the range between C to infinity, that is in this range, and the motion is aperiodic here. The motion is aperiodic, and it decreases until the minimum C is found, right? The motion is aperiodic and decreases until a minimum value at R equal to C is achieved. Okay, achieved. Basically what I'm writing here is that the minimum of the kinetic energy in this range C to infinity is achieved at the point C, and as you go farther and farther away from C, the velocity of the speed of the particle increases, the R dot increases, and it increases without bound, right? So that's the case. Okay, so then let us come back to our discussion on planetary motion. So here we have tried to summarize our results and try to compare our results of 2D with 1D here. So let us go back to our 2D planetary motion. So what exactly we are trying to say is, let us say that we have the planet. So again, let us call the center of the motion to be O, that is where the sun is situated. And let us say that the planet is located here at some distance, right? And let me just say that the planet is traversing an ellipse, right? So this is going around an ellipse, right? And so the ellipse has two axes. One is the minor axis, one is the major axis. So let me draw two circles, one about the minor axis, and of course one about the major axis, which is this large one, right? And we see that the motion is the path or the trajectory of the ellipse of the planet is along this ellipse, right? And what we have is that this is alpha, and this is our what have we got? There is something more that I need to show, which is the following. Okay, so what have we got here is the following. Okay, and so on. Okay, so what we are showing is that notice that in this planetary motion, the way it is achieved, so we are talking about the planetary motion in the case when the energy of the system is bounded. So we are talking about the bounded case, that is the bounded orbit case. Okay, so again, let us try to recap. We looked at two possible scenarios in the 1D energy equation or the energy conservation equation, the bounded motion and the unbounded motion. So in the bounded motion, we expect the planetary motion to be performing an elliptical orbit, right? And let us see more details about this elliptical orbit, which is as follows. So in the bounded orbit, the orbit touches the the inner and the outer circle alternatively. And what we see that the radial coordinate r is between A and B, right? So the radial coordinate r is between A and B. So suppose, so what have we got? So suppose the particle P, is at B1. So what is B1? B1 is, let us say that B1 is this particular coordinate B1, and these are the points of the trajectory A1 and then A2 and so on, right? So suppose the particle is at B1 and OB1 is the line at theta equal to 0. So OB1 is the line at theta equal to 0, and this is at t equal to 0, right? So OB1 is where the particle is at t equal to 0. So this is my reference baseline of the motion. Okay, so then we expect that we need to number the equations here. So this the derived equation here is 2 prime here, which is the 1D equation. So in the energy equation 2 prime, we see that r dot is an even function of this kinetic energy, is an even function of r dot or velocity, right? So we are going to utilize this information. So since from 2 prime, since r dot, or since r is an even function of t, we have that the segment B1 A2 is just the reflection of A1 B1 about the line OB1, right? So since r is an even function of t, the segment A1 B1 A2 is just the reflection of A1 B1 about the line OB1, right? Because of this information. So we have that this particular length of the segment A1 B1 is the same as the length of the segment A2 B1. Okay, so then further what we have is that we expect that the angle here, which is subtended by the arc OA1, is the same as the angle which is subtended by the arc OA2. So we have that angle A1 OB1 is the same as the angle B1 OA2, right? Let me call this as alpha. And then what have we got here is, so similarly, we expect that there is a similar form of motion. We expect that A2 B2 is the reflection A2 B2. So we need to define. So here the third point is B2 here, where it touches the larger circle. So A2 B2 is just the reflection of A1 B2 of B1 A2 about OA2, right? So A2 B2 is just the reflection of A1 B2 about the line OA2. And what have we got here is that the length of the entire orbit is an integer multiple of the segment A1 B1. Okay, so if we continue, if the planet continues the motion in a way that the segments are of equal length, that is A1 B1 is the same as A2 B2 is the same as, sorry, A1 B1 is the same as A1 B1 A2 is the same as B2 A2 and so on, we expect that the length of the entire orbit is an integer multiple of the length of one segment, right? And also further, the you know the radius that these lengths subtend, they subtend an equal angle alpha everywhere, right? So we expect that the next point of touching this inner circle will be such that we have again an angle alpha which is subtended by this planet. So notice that uh, typically what we expect is, if this is the motion of the planet where the angle subtended is always constant and the length of the sector, based on the Kepler second law, the length of the sector is always the same, we expect that the orbit may not be closed in one revolution, right? And we will see that typically this is the case of planetary motion. In many, almost in hardly there is a case where the orbits are closed, right? So this is what we are trying to show. Although the orbit is bounded, the orbit will be closed. The orbit is bounded, it is closed if some integer multiple of alpha. So although the orbit is bounded, the orbit will be closed if some integer multiple of alpha is going to be some whole number of complete revolutions. Well, I need to write this entire statement in a more concise fashion, so I'll do that in just a moment. Some whole number of complete revolution. Complete revolution. Okay. So what have we got here is that alpha is some integer multiple of 2 pi, right, where this is an integer. Okay, well, this is not an integer but a rational number. Okay. So what we expect is that the angle that this arc subtends must be some rational number times the value of complete revolution, which is 2 pi. Okay, so that is when we expect that the orbits will be closed. Otherwise, we expect that orbits will never be closed. Okay. It turns out that there is an exception to this bounded orbit not being closed. The bounded orbits will always be closed if we are talking about, when we are talking about the central fields being an inverse square field, right? So what we have is that the bounded orbits are closed in case of inverse square fields. The bounded orbits are closed in case of inverse square fields, and that's it. Okay, so then let us now look at well, what have we got? Let us define some terminologies for all these motions, right? So here we see that in this diagram there are certain distances from the center O which are very close to the center O, and there are certain distances of the planetary motion which are the farthest from the center O. So these are the closest and the farthest distance of the planetary motion are known as the so-called apse. The apse of, or the apsidal distances of the planetary motion. And the angle, the equal angle that these apsidal distances subtend is the so-called apsidal angle. Right? So the terminology is as follows. Apse is apsidal distance and apsidal angle. apsidal angles. Okay. So what we have got is a point of an orbit, at which the distance OP, well, what is OP? Well, we are talking about the distance OP. What is this distance OP? We talk about O being the center and P being the planet itself. So the distance OP achieves its minimum, or achieves its maximum and minimum, is called an apse of an orbit. An apse of an orbit, and these maximum and minimum distances are the so-called apsidal distances. Right? These maximum and minimum distances are the apsidal distances, and the angular displacement between successive apses is the angle alpha. Right? So this is the angular distance, and the angular displacement between the successive apse is the angle alpha, or the so-called apsidal angle. Okay, so that's the terminology here. Okay, so then for Sun, these apsidal distances have special names. For Earth also they have special names. So for orbits around Sun, these minimum and the maximum apsidal distances are known as the perihelion and the aphelion. The perihelion and the aphelion, and for orbits around the Earth, this minimum and the maximum distance is the perigee and the apogee. Okay, are the perigee and apogee. So then, these apses, they are special because these are the minimum and the maximum distances from the center, right? From the center O. So when we talk about minimum and maximum, there is some sort of a derivative involved, and the derivative is taken to be 0. So it turns out for at an apse, we have that the derivative of r, or the velocity, the radial velocity, is 0. Right? And hence from energy conservation, we have that Vr plus L square by 2 pi square is equal to, L square by 2r square is E. Right? So since there is no kinetic energy at the apse, the total potential energy is equal to the total energy of the system. So that's the total potential energy. Right? So then, which means that this is the equation. Let me call this equation number 3 here. So 3 provides us the apsidal distances, which are the positive roots of 3. Okay, so we solve this equation number 3 to get the apsidal distances, the positive roots. Okay, so let us look at an example related to this discussion that we had. The example is as follows. I think the example is a little bit long, so let me just take a very brief a gap, and we'll discuss this example in the next module. So thank you very much so far for listening. Thank you.